Deploying a decentralized protocol into the wild exposes a brutal truth. Theoretical network models fracture the moment they touch real-world topography. This dashboard tracks a 50-megabyte payload navigating mixed NAT testnets, consistently completing within a 65 to 74-second window. A secondary metric tracks manipulation. When a node subverts the system, its trust score plummets past a critical threshold and flatlines, resulting in permanent isolation. No human administrator flagged that node. There is no central policing authority monitoring these connections. Hitting these speeds while simultaneously executing automated defense is the direct result of a completely overhauled transport layer and an algorithmic trust engine. The question is how a permissionless network executes this, dynamically isolating misbehavior and scaling data throughput without any central coordination. True decentralization relies on an architectural framework capable of ruthlessly policing itself. To understand how the network processes 50-megabyte payloads at those speeds, we have to start at the foundational transport layer, the physical bedrock of data movement. When peers interact in a real-world mixed NAT environment, three dominant failure modes bottleneck the data. The first was relay tunnel intermittence, where unstable routing caused connections to drop entirely during mid-transit. The second involved clock skew tolerances falling out of sync between distributed peers, running different release branches, causing nodes to reject otherwise valid data. This topology map demonstrates the solution for node overwhelming, backpressure handling. When massive data creates a bottleneck, the system dynamically throttles the upstream flow. By pairing this with strict delivery acknowledgements, data releases only when confirmation signals navigate the return path, guaranteeing arrival. Patching these transport pipes eliminates intermittent connection failures that blocked large file transfers in early testing. However, ensuring data moves reliably is entirely separate from ensuring that data is valid. Guaranteeing data integrity requires a dedicated cryptographic state verification mechanism. Before the network finalizes a payment for storage, it must physically verify the data's state. This introduces the third production failure mode, misbehaving nodes issuing bad quotes to the client during upload attempts to claim unearned payment. This Merkle tree visualizes the defense, verifying Merkle chunk closeness. It calculates the mathematical distance between a data chunk and a storage node. If a node issues a bad quote, the client uses this verification to reject the claim, failing the mathematical proximity requirement. Standard file uploads running through the desktop application now rely entirely on this logic to process reliably. Binding payment formalities strictly to Merkle chunk closeness removes the mechanical ability for malicious nodes to profit off falsified storage claims. The most complex variable in any network is the operator. In production, long-term node operators actively run modified setups to test boundaries and bypass system constraints. A specific exploit emerged recently where nodes crossed their identity keys and generated manipulated quotes. The autonomy philosophy is absolute. The team will not police the network. The protocol must absorb the attack and neutralize the threat independently. It executes this through the EigenTrust engine, operating as the deterministic arbiter of network participation. When a node transmits a foreign cryptocurrency key, the system detects the mismatched signature. A strong negative trust event tanks the offending node's integer score. Dropping below the swap threshold triggers an algorithmic eviction, physically severing the penalized node's connections and cycling it out. The system also maintains a self-healing recovery path. Honest peers who correct their configuration naturally rebuild their trust score and rejoin the network within about a day. This dynamic, bias-free trust engine translates malicious math into immediate operational exile, providing the security layer required to maintain a live network. Resolving these Layer 1 transport and trust barriers is strictly a prerequisite for unlocking massive throughput at the application layer. The Reading Room production server showcases exactly what the indelible SDK can handle. This chart maps the specific scale-up metrics. We are moving from a baseline of 300 enriched papers directly to a 10,000 paper ingestion pipeline this month. The updated indelible SDK permits file ingestion via API token, allowing organizations to achieve massive scale for immutable, unedited data preservation. Simultaneously, the X0X soak testing pushes extreme parameters, maintaining millions of subscribers per pub sub topic. This throughput enables an architecture called Agent Symphonies, a synchronized swarm of specialized agents executing high-frequency, coordinated movements entirely without a central leader. Right now, X0X operates as its own secure test harness, proving these specialized agents can coordinate on complex tasks across distributed machines. High-throughput applications and autonomous agents can only function at this scale because they operate on top of a self-policing, back-pressure-resistant foundation. When assembled, these elements form a unified operational stack: the physical transport layer, the trust engine, and the application layer. At the base, transport backpressure and Merkle verification ensure data integrity. In the middle, the EigenTrust engine provides an automated security perimeter against active exploits. This stack prepares the network for an impending reality. Soon, the auto upgrades will cease, and the development team will step away entirely. When the central authority disappears entirely, the decentralized network will rely strictly on these autonomous protocols to survive and scale. A decentralized system is only as viable as its programmatic ability to verify, punish, and self-heal in real time,